session of yesterday's 2 hours lecture in the compulsory instrumental analysis course. The last topics is X-ray analysis and surface analysis, electron surface analysis. Only two topics were mentioned in the syllabus, SPPU syllabus. So the second content, yesterday I was finished with the X-ray diffraction, and today I will begin with the X-ray photoelectron spectroscopy, and I will finish with this X-ray photoelectron spectroscopy techniques, fundamentals, basics, and their applications in the research materials. Okay. This is yesterday's once again first slide. This Rayleigh scattering or elastic scattering that was concerned with respect to diffraction, X-ray diffraction. This is another technique, X-ray fluorescence technique. Compton scattering is another technique. So today, because of incident X-ray, when it interacts with the constituents, particles, atoms, ions, this is a nucleus, and when it interacts with the core cell, preferably, that X radiation is having energy enough to eject the electron from the core cell, and with the help of instruments we can measure the kinetic energy of ejected photoelectrons. Therefore, this technique is called as a X-ray photoelectron spectroscopy. So what we measured the kinetic energy of ejected photoelectrons by interaction of monochromatic X radiation, which is having high energy, and preferably with the core electrons, it has a energy enough to remove the electron from core cell. That electron is called as a photoelectrons. So this technique is called as a photoelectron spectroscopy because we are measuring the energy, kinetic energy of ejected photoelectron by the incident of X radiation. So that's why this technique is called as a X-ray photoelectron spectroscopy. Sometimes what happens, along with the photoelectrons, a secondary electron is also ejected. While after ejecting the core cell electrons, the systems becomes unstable, and to become a stability, the next cell electrons jumps to fill the vacancy, and again energy difference is observed in the system. So to maintain the energy difference, next valence cell is electron is ejected. This was discovered, phenomenon was discovered by Auguste Auger, and to honor the Auguste Auger, this electron is called as a Auger electron. So this is also spectroscopy, X-ray spectroscopy, but it is called as a Auger X-ray electron spectroscopy. So we can get in the spectra even photoelectrons intensity also and Auger electron intensity also. So we should have a technique to identify which is photoelectron and which is Auger electron. So this is a basic principles behind X-ray photoelectron spectroscopy. This is yesterday's slide, but a little bit I had modified that. This X-ray diffraction, the principle and two application that I was explained yesterday in the throughout 2 hours lectures. Similar to X-ray diffraction, this X-ray photoelectron spectroscopy has a lot of application in surface chemistry, identification of chemical bonding, identification of chemical state, and elemental analysis we can perform in the thin film of solid substances. That are the applications we are going to discuss today after understanding the principle of X-ray photoelectron spectroscopy. So, what is a X-ray photoelectron spectroscopy? It is concerned with the measurements of kinetic energy of photoelectrons, which is emitted preferably from core cell of atoms from any material by the irradiation of X-ray. Advantage of this technique is very sensitive on the surface layer up to 10 nanometers. Below the 10 nanometer, uh, estimation is not possible. That X radiation cannot penetrate from the surface solid material below the depth of 10 nanometer. So therefore, this technique has an advantage to detect the surface phenomenon. The technique is more sensitive up to 10 nanometers. The below figure shows that these are the three common surface analysis techniques which are used in the research. The first one is a X-ray photoelectron spectroscopy that we are talking about. Second one is one type of mass spectroscopy, which is called as a secondary ion mass spectroscopy. And third one, which is exactly similar to X-ray photoelectron spectroscopy, but the electron ejected because of agar emission. So that spectroscopy can be also useful for surface analysis. So what is the difference and which technique is more sensitive? If you compare these three techniques, photoelectron spectroscopy, secondary ion mass spectroscopy, and agar electron spectroscopy. If you see this figure I took from one of the review research paper. The analysis depth of these three techniques is given, and X-ray photoelectron spectroscopy, we can analyze the sample up to the depth of 10 nanometer. For secondary ion mass spectroscopy, we can analyze the sample up to only 1 nanometer. The scale is given over here. This line indicates that it is up to 1 nanometer. And agar electron spectroscopy, we can do estimation up to 10 nanometers. Up to 10 nanometers. So depth-wise, XPS and AES is more superior than secondary ion mass spectroscopy. But if you compare the relative analysis area, from which length to which length, what should be the sample size, broadness of the sample, then we can analyze with the help of X-ray photoelectron spectroscopy with the analysis area up to 10 micrometer. That sample size we can analyze with the help of X-ray photoelectron spectroscopy. With the help of secondary ion mass spectroscopy, we can analyze only up to 100 nanometer analysis area. And in case of agar electron spectroscopy, we can analyze the diameter or analysis area of the sample only 10 nanometer. So this 10 micrometer, 100 nanometer and 10 nanometer, out of that 10 micrometer is a bigger size. So therefore, this X-ray photoelectron spectroscopy is a more sensitive compared to the another two techniques which are normally used in the sample material analysis or surface analysis. Okay, so this is a basic fundamentals or principles related to X-ray photoelectron spectroscopy and up to which depth the sample analysis can be carried out with the help of X-ray photoelectron spectroscopy we can perform. And applications are in surface chemistry. So surface chemistry is not concerned only with the crystal structure. Surface chemistry is not only concerned with the crystal structure. We can find out the surface, we can study the surface chemistry for amorphous substances also. We can study the surface chemistry of polymer material also. We can study bio material also. So it is applied for all areas of science, not only in the crystallography. This X-ray photoelectron spectroscopy is not only for crystallographic techniques, but X-ray diffraction is only crystallographic techniques, which are useful only to analyze the crystal structure. So that is a more advantage of X-ray photoelectron spectroscopy compared to X-ray diffraction. Why this is called as a spectroscopy and X-ray diffraction is not to be called as a, not supposed to be called as a spectroscopy, because X-ray diffraction is concerned with the elastic scattering, and the frequency or energy of scattered radiation in the diffracted beams is identical to the incident X-rays. So therefore there is no change in energy, and we cannot call it as a spectroscopy. It is just to be called as a diffraction, X-ray diffraction. But we can call this photoelectron techniques, X-ray photoelectron technique, as a spectroscopy because of interaction of X radiation. The emits the photoelectron, and the energy of photoelectron is different than energy of incident X-ray. So change in energy is observed, and that's why we call this technique as a spectroscopic technique. Okay, so we will switch over to next slide. Any doubts with respect? Okay, नहीं आ रहे अभी? Can you hear me? लेकिन सर ने मेरे लिए वहां लगा के Okay. Everyone see the slide? Yes, sir. Okay. Because electricity went for just 2 minutes. I thought that. Okay. Now we will go to detailed techniques. What is a X-ray photoelectron spectroscopy? Previously, this technique was called as a electron spectroscopy for chemical analysis. This X-ray photoelectron spectroscopy was formerly known as a electron spectroscopy for chemical analysis. Particularly, this technique was used for only surface analysis. But nowadays, this ES electron spectroscopy for chemical analysis, ESCA, normally it is pronounced as ESCA. This technique, XPS, is useful for the chemical state analysis also, quantitative analysis also. So therefore, the name ESCA is replaced as a X-ray photoelectron spectroscopy rather than electronic spectroscopy for chemical analysis. Okay. This is the incident X-ray, and I told you that is a surface phenomenon. We can estimate the surface sample only by X-ray photoelectron spectroscopy up to the 10 nanometer depth. So this is one atom, second atom, third atoms, nucleus, electron. This is core electron. This is valence electron. So electron is ejected. The energy of X-ray is more. So it has a capacity to remove the electron from core cell. And these are the beams of photoelectrons. And these photoelectrons is detected in different types of analyzers or detectors in the X-ray photoelectron instruments. So the detected, the kinetic energy is detected, or kinetic energy of ejected electron is measured. So how this technique is useful for estimate analysis. There is one mathematical formula over here. This h nu is nothing but the energy of incident X-ray, which is given by Planck's equation. Planck's constant multiplied by frequency of X-ray. It should obey the law of conservation. That should be equal to kinetic energy, which is measured by the instrument, plus binding energy. So what is the binding energy, that I will explain. And one more mathematical symbol is there. That symbol is called as a work function of the instrument. That I will explain on the next slide. What is the work function of the instruments? So the kinetic energy of electrons, the electron is coming from the surface and it has a different speed. So the kinetic energy of electron by classical mechanics, you are familiar with the famous equation, half into mass into square of the velocity. We got the kinetic energy of electron. So electron reaches towards the detector or analyzer, and the kinetic energy of ejected electron is measured. What is the binding energy? The binding energy is a very important property or characteristics of each electron in a given atomic system. Every electron has different binding energy. So the amount of energy required to remove the electron from system up to Fermi level. Up to Fermi level. Later on, I will explain what is meant by Fermi level. That is called the binding energy of electron. So every electron has a binding energy, whether it is bind in core shell or bind with the valence shell. Every electron has a different energy, and you are familiar with the in the concept of electronic configuration. You write the electronic configuration 1s2, 2s2, 2p6 like that. So 1s electron, first field, then 2s electron. So accordingly, the energy increases. But the binding energy decreases. The energy of electron increases, but the binding energy decreases. So that is called as a binding energy. Amount of energy required to remove the electron from system to Fermi level. That energy is called as a binding energy of electron. So in this technique, if there is a core shell electron, its binding energy is different. Next core shell electron, 2p electron, binding energy is different. 3p electron, binding energy is different. So every electron has a binding energy, and that is a basic principle for identification of any surface properties of any material. And what is the work function? For that, I'm going to explain next one more slide. But before that, there is one more mathematical equation written over here. That is a rearrange equation. We are concerned with the binding energy because we are talking about the surface properties of material. So we are familiar, we must know what should be the binding energy. So when we know the incident radiation energy, X-ray energy, and when we the instrument measures the kinetic energy, and when we know this constant, which is a spectrometer's constant work function, then the instruments automatically subtract total energy of incident radiation minus kinetic energy minus work function. That gives the binding energy. So we can directly find out the binding energy of each and every electrons from the constituents atoms or that molecules, or whether it is a polymer compounds, or whether it is adsorbent, or whether it is a crystalline substance or amorphous substance, or inorganic compounds or organic compounds, that can be easily identified by using X-ray photoelectron spectroscopy. Once again, I will go in detail again to understand what is the work function, what is kinetic energy. So if you see this slide, photoelectron is ejected from the system. So this is in electronic configuration level. So this is a core shell electron, 1s2, 2s2, 2p6. Then next we call normally in the material which is called as a valence band. Then next there is a level which is called as a Fermi level. Next is a conduction band, and next is a free electron level. Next is a free electron level. So when X radiation is incident having energy by Planck's equation H nu on the any surface material which has a sufficiently to eject the electron from core cell. So core cell electron is ejected from the system and it will travels towards the detector or analyzer. And the kinetic energy of these photoelectrons is measured with the help of instruments. Now here I am telling you that what is meant by binding energy. So it is the minimum amount of energy required to remove the electron from any cell up to Fermi level. Up to Fermi level. This much amount of energy is nothing but the binding energy of that particular electrons. What is Fermi level, that I will explain. And from every instrument has a tendency, or it has some energy, it requires some energy to transport the electron from Fermi level to free electron level or vacuum level. How much amount of energy is utilized from the incident X-ray? That energy is nothing but the work function of the instrument, work function of the instruments. And rest of the energy is carried along with the photoelectron, which is called as a kinetic energy. So this H nu, total incident energy, some of the energy is utilized to remove the electron from core cell to Fermi level. Some of the energy of X-ray is utilized for to transport the electron from Fermi level to free electron level, and rest of the energy is carried along with the free electron, which we measured in the photoelectron spectroscopy as an kinetic energy. So this technique in depth, that what is the X-ray photoelectron spectroscopy. So what is this Fermi level? It is a level, energy level, one energy level, which is occupied by the electron orbital at absolute zero temperature or absolute Kelvin temperature. So from this level, valence band, from this level, the energy, electron has a definite energy, occupied energy. Above this level, the electrons comes into the conduction band, and it does not have any specific energy level. So such type of level is called as a Fermi level. So this part is concerned with the photoelectron emission, how photoelectron emission works, and what is principle, why the binding energy is equal to incident energy minus kinetic energy minus work function of the spectrometer, what the instrument we use. This side is nothing but the agar electron spectroscopy. So what is the agar electron spectroscopy? When X radiation is incident and core cell electron is ejected as a photoelectron, there is a vacancy is created in the core cell, system becomes unstable, and everyone wants the stability, whether it is in the solid state or liquid state or gaseous state. So to become a stability, the electron from valence cell or next cell jumps from next orbit to inner orbit or core cell orbits. And again, energy difference between these two electrons is not equal to the incident energy, and therefore some of the rest energy, another electron from valence cell is ejected, and such electron is called as a secondary electron or agar electron. So that spectroscopy is called as a agar electron spectroscopy, and we can measure the kinetic energy of this agar electron. But the kinetic energy of this agar electron definitely less than the photoelectrons. Sometimes it may be the greater than the photoelectrons, depending upon system to system, or varies from system to system. So such type of agar emission, you will find in the research paper the notation in the spectra KLL. agar emission is there, but it is denoted as a KLL. Photoelectron is emitted from K cell, and electron from L cell jumps to fill the vacancy, and another electron is ejected from the L cell, which is a agar electron. So that's why it is called as a KLL agar electron. KLL agar electron. Okay, is that clear? Any doubts about these techniques? How the electron is ejected from the system at microscopic level? Any doubts, student?
No, sir.
Okay. So next, we will switch over towards the instruments now, because course title is a instrumental analysis. So after the principle, how the analysis is carried out, that you must know. Normally, like X-ray diffraction, the source of X-ray is a X-ray tube, which is anodes and cathodes, and anode is made from the either magnesium or aluminum or tungsten or copper also. So if it is a magnesium anode, and if it is a K alpha, what is K alpha, that I was explained yesterday, whose energy, if it is a monochromatic, whose energy in electron volts is 1253.6 electron volts. And if it is aluminum K alpha, which gives more energetic X-ray, whose energy is a 1486.6 electron volts. So this is cathode, this is anode, this is cathode, this is anode. And for example, the anode is made from magnesium and X-ray is emitted, then it is called as a magnesium K alpha. If the anode is made from aluminum and X-ray is emitted from aluminum, then it is called as a aluminum K alpha 1 or K alpha 2 or K beta 1 or K beta 2. That I was explained yesterday. So this is a X-ray tube. That is an incident radiation. That's why it is called as a X-ray. Then this is a sample. When the sample emits the photoelectron, so this is a way to travels the photoelectrons. It focuses with the help of lens into the one hemispherical analyzer. Hemispherical. There are different types of analyzer in X-ray photoelectron spectroscopy. Hemispherical or cylinder or circular or semicircular. That type of analyzer is there. So this is a spherical analyzer in which there are again two electrodes, spheres, two spheres. One is positive and one is negative. And through this hemispherical analyzer, the photoelectron transports towards the electron detector. Electron detector detects the energy of that particularly kinetic energy of that particular photoelectrons, and by using computer algorithms, we got the spectra, like NMR spectra, like ESR spectra, like UV spectra, like FTIR. We got the spectra. That spectra is called as a X-ray photoelectron spectra or spectrum. So this is a basic instrumentation related to this particular X-ray photoelectron spectroscopy. Most important requirement for this particular instrumentation is it requires ultra high vacuum. The whole assembly from this system to electron detector system, whole assembly of this system is completely evacuated, and it should be created by ultra high vacuum. The reason behind that, whenever X-ray travels in any air medium or electron travels in any air medium, they collides with the nitrogen or oxygen gases which is present in the atmosphere, and they may lose their kinetic energy. And to detect properly, the system should be completely evacuated. What is meant by completely evacuated? The system should be ultra high vacuum. So what is meant by ultra high vacuum? The ultra high vacuum, if the pressure of this particular instrument, that assembly, is greater than 10 raised to minus 7 millibar, then that vacuum is called as a ultra high vacuum. High vacuum is there, medium vacuum is there, low vacuum is there, depending upon pressure. So as far as possible, the system is completely evacuated and it should be ultra high vacuum to measure the photoelectron kinetic energy correctly. That is the purpose of this getting the ultra high vacuum in the instrumentation of X-ray photoelectron spectroscopy. So, in addition to this system, we required in the instrument some special type of pump, rotary pump or turbomolecular pumps, or in addition to turbomolecular pumps, baking with 120 degrees Celsius, which gives a pressure greater than 10, sorry, smaller than 10 raised to minus 9 millibar. Or using some another technique, titanium sublimation pump can be also used to get a more and more vacuum to record the correct kinetic energy of photoelectrons. So this is a most important condition in the X-ray photoelectron spectroscopy. Any air media or any material which is present, that will interfere in the analysis technique. And nowadays this is possible to create ultra high vacuum in the instrumentation techniques. So today we use normally X-ray photoelectron spectroscopy. Before 20-25 years, to create ultra high vacuum was difficult, and at that time, instead of X-ray photoelectron spectroscopy, UV photoelectron spectroscopy was used, where the energy of UV radiation is less than energy of X radiation. Since it has a certain limitation, that energy is less means photoelectron emitted will not be from core cell, it may be from the valence cell of that particular atom. And therefore, there are so many valence cell of each atoms, and there is a overlapping of kinetic energy of that electrons in UV photoelectron spectroscopy. So that problem was resolved by using X-ray photoelectron spectroscopy. Okay, we will go to next slide. This is about the instrumentation. Now, how we got the spectra in the spectrometer? This is one of the XPS spectra, where this is a basic equation, that conservation equation, energy conservation equation. And here the spectra is recorded by using aluminum K alpha source, aluminum K alpha X radiation. On y-axis, the number of electron counts is recorded, or intensity is recorded. The number of counts in terms of electron is recorded. And on x-axis, there is an increase in kinetic energy. From here, for this particular spectrum, it is showing 80, but it should start with the 0. 80 electron volts, it has a units of electron volts. 80 electron volts to 1480 electron volts. So this number indicates that this X-ray source is a aluminum K alpha. If this number is up to 1250 in the scale, which indicates that this particular source of X-ray is less powerful than aluminum, which is a magnesium K alpha. So the kinetic energy is measured by the instrument, but we are familiar in chemistry or in science with the molecular level or atomic level about the binding energy. So this kinetic energy is related to binding energy. When we know the energy of incident X-ray, instrument measures the kinetic energy. The instrument has a constant work function. We can find out the binding energy. So by again algorithm methods or by using some small calci in the instruments calculator method, we convert that kinetic energy into binding energy. So binding energy will be equal to incident energy minus kinetic energy minus work function. So binding energy and kinetic energy are inversely proportional. So this next scale on x-axis is concerned with the binding energy. 80 is replaced by 1400, and here 1480 is replaced by 80 or 0. So if you study the photoelectron spectra in terms of kinetic energy, origin value will be the smallest. But if you find out, convert the kinetic energy into binding energy, instrument convert the kinetic energy into binding energy, then the origin of that particular spectra or spectrum started with the highest kinetic energy, and that should be the identical to the energy of incident X-ray. So this way, the spectra is recorded. Here you can find less intense peak. This is another peak. This is another peak. This is a two peaks. This is a small peaks. This is a two peaks. One is having less intense. Another is having more intense. So such type of intensity, different intensity line is observed, like IR spectra, FTIR spectra, or Raman spectra, or NMR spectra, or ESR spectra. Such type of spectrum, UV spectra or visible spectra, we can observe on the photoelectron spectrum. Okay. Now, after this is just fundamentals related to X-ray spectrum or X-ray photoelectron spectroscopy. How we analyze. Now, again, we will continue to some important fundamentals. See the next slide. This slide is the same spectra, previously spectra. This spectra is a X-ray XPS spectra of pure nickel metal, solid nickel metal. And nickel is a transition elements. You are familiar with their electronic configuration of nickel, how electron is distributed in the nickel. Electronic configuration, everyone knows how to write. This is a nucleus, 1s subcell, 2s orbital, 2p orbital, 3s orbital, 3p orbital. Next of this 4s. Next is 3d, and so on. So electron in the nickel atom metal is distributed from 1s to 3d. And this distribution we did by using Abbo's principle and Hund's rule that everyone knows. Now, in this electron, when X radiation is incident, which is having energy, it interacts possibly all electrons. It interacts possibly all electrons. So, this valence electron, for example, assuming that this 3p electron is a valence electron, 3s electron is the next cell which is inner, 2p is the next which is inner, 2s is the next, and 1s is a core cell. So electrons, we cannot give the commands to X radiation, don't interact with the valence electron, or don't electrons with the 3p or 3d electrons. We want to study proper X-ray spectroscopy. So electron can interact with this electron also. X-ray can interact with all subcell electrons, and each electrons transports through Fermi level to free electron energy level, and it enters into the detector or analyzer of that instrument. So we got each electron has a different kinetic energy. So kinetic energy is recorded by instrument. That kinetic energy is converted into binding energy. So this electron has a different binding energy. 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 So this measured binding energy, in short, directly kinetic energy, each electrons has a different intensity, different number, different population. So that's why we got different peaks in the X-ray photoelectron spectra. So we cannot say that we will get only one lines in the spectra, which will be the 1s electron. That will not observed in the spectrometer. We get a whole spectra with the binding energy 0 electron volts to 1400 electron volts. So, how to analyze this one? These peaks is having lower binding energy, and these peaks is having higher binding energy. So, can you tell me that this higher binding energy is for core shell electron or valence shell electron?
Core shell electron.
Good. So it is a core shell electron. So why it is having more binding energy? Because they are very close to the nucleus. Nucleus consists of proton. Proton is positively charged particle and electron is negatively charged particle. So this core shell electron is very close to proton. So there is a strong attraction between this electron with the proton compared to the next shell electron, compared to the next shell electron, compared to the next orbital electron. So therefore, the binding energy decreases from inner core shell to outer shell. This is a strategy to identify which peak will be likely for nickel. This will be for which nickel electron. This will be for which nickel electron. This will be for which nickel electron, which core shell electron, p orbital electron or s orbital electron, that we can easily analyze with the help of X-ray photoelectron spectroscopy. Okay, we'll go to next slide. Now, here I have quoted some of the binding energy of electrons. This 66 electron volts, close to zero. This peak is because of electron is ejected from 3p orbital. The next, this 110 electron volts, the electron is emitted from 3s orbital. Here I have not mentioned anything because it is not concerned with the XPS. Next, most intense peak electron is 852 electron volts, which is from 2p electrons. It has a doublet like NMR spectra. Later on, I will give you how it gives doublet. And this 2s, which is again having more binding energy, 1008 electron volts. And here there is no any peaks. No any peaks, still 1400 electron volt binding energy. Which means that to remove the electron from 1s cell of nickel metal, it requires more binding energy from 1400 electron volts. So if the atomic size increases, the number of cell increases. So in this case, this will be the core shell electron, but this will not be the core shell electron. So this way, if it is a carbon, then easily carbon 1s electron can be easily removed. But if you go from higher and higher atomic number, the electronic configuration, the electrons energy increases. So size increases, X-ray cannot penetrate up to the core shell electron, and therefore the kinetic energy of that core shell electron is greater than the incident energy. If the energy is greater than incident energy or binding energy is greater than incident energy, then it will not observed in the XPS spectrum. Now, I'm going to explain what are these three peaks, which shows somewhat doublet. In the next, see that how these energies, how I got this number, 852, 110, 66 electron volts. So these numbers In 1999, the binding energy of XPS instruments at international level is available in the literature data, and that books was published as a handbook of elements and native oxides. What are this table, this handbook table? This first column consists of three sub-column. This one stands, it is a binding energy, 1 electron volts. This is the element bismuth, whose binding energy is 1 electron volts, and the which is electron 6p electron has a binding energy of bismuth having binding energy 1 electron volts. There are so many elements having binding energy 1 electron volts, but all these orbitals are valence shell orbitals. All these are the valence shell orbitals, so which requires less amount of energy to remove the electrons. So therefore, their binding energy is less. So this handbook is available. Again, in the latest technology, the XPS instrument has this data already for each sample. So directly, like XRD's XRD indexing, directly we can do the indexing by comparing with the binding energy of unknown sample with the binding energy of known sample. So it starts with 1 electron volts, and all these are the chemical elements which is present in the periodic table or known chemical elements. This is a second page, started with 82 electron volts, end with 275 electron volts. Third page of handbook, 278.7 electron volt to 609.1 electron volts. And each binding energy has different constituents or different electrons, which is mentioned in the third column with respect to that. So this is available as a handbook is available in the literature. This last fourth page starts with 609 electron volts and end with the close to aluminum X-ray energy 1395 electron volts. So from this table, 1 minute. From this table, I had denoted these peaks, 66 electron volts. Then this 66 electron volts compare with this 66 number, 66 electron volts. This is 66 for nickel and having 3p electrons. Binding energy of nickel having 3p electrons. So we must know some properties of that elements, that we know that the sample is nickel. So nickel peak will be there. So this way, this spectra, this peaks is analyzed 3s electron, 2s electron, 2p electrons. This is not analyzed over here, doublet, and this is not analyzed. So what are these central peaks? These central peaks from this region to this region. These because of agar electron emission. And this electron is also reaches towards the detector. We cannot filter that electron. It will enter into the photoelectrons, proper photoelectrons, secondary electron, this. And this also gives some peaks. One peak, second peak, third peak. So this agar electrons data is also available. Say for example, 640.42 electron volts. This is for nickel. So 640.42 electron volts. You can see here 640.4 electron volts. Nickel, and here in the literature, this electron is a agar electron. So this data is available in the literature. This data is concerned. Another case that I will show you, that this manganese, you can see, sorry, this manganese 640.9, 641, 641, 641.6 If manganese is Mn3O4, it has a different binding energy. Manganese in manganese oxide, MnO, different binding energy. MnO2, different binding energy. Which means that the oxidation state of the manganese can be also analyzed by X-ray photoelectron spectroscopy. So that's why in the first slide I had showed in the application, we can analyze the chemical state of the elements can be analyzed with the help of X-ray photoelectron spectroscopy. So this way, we can analyze X-ray photoelectron spectrum for any of the pure sample, impure sample, or complex sample, inorganic sample, organic sample. Preferably, the sample should be in the solid state or semi-solid state. Semi-solid can be analyzed with the help of X-ray photoelectron spectroscopy. Next, this is a XPS of sodium chloride, pure sodium chloride. And you can see that here peaks are observed. Sodium chloride consists of sodium atom also and chlorine atom also. So you can see that this is peak of sodium 2p, sodium 2s, which is having less binding energy. They are the valence electron. Then sodium 1s, which is core shell electron, which is having very high binding energy, 2 electron volts. Then chlorine 2s, chlorine 2p, which is having binding energy greater than sodium, because atomic size increases, binding energy increases. This 2p and this 2p is having different binding energy because this is sodium and this is chlorine. This is the electron from 2p and this is the electron from 2b. The binding energy of same level electrons. But one is sodium atom, one is chlorine atom. And the binding energy difference, that elemental shift from sodium to chlorine, is 30 electron holes to 200 electron holes. So difference is very big, 170 electron holes. That much more energy is required to remove the electron from 2p in case of chlorine compared to the sodium. 2s is again more core towards the nucleus, which has more binding energy. This is again agar electron of sodium. K shell electron is ejected and agar electron is ejected, which has a binding energy. So this way, from the literature data, the peaks can be analyzed, samples can be analyzed. Here also there are more peaks, which is not I have analyzed, which we can analyze. So sodium 1s, this sodium 1s is because of X-ray photon induced emission, and sodium KLL is because of XPS induced agar emission, means it is a secondary electrons. Secondary, we can say it is a secondary electrons emitted from the sodium metal or sodium chloride crystals. Next, in terms of energy level, normally we know the vertical. In case of sodium, in the previous slide, sodium 1s, this is a sodium 1s electron, 1s2. When X radiation is incident, the electron is ejected, and till this level, the electron system, it comes outside the system. The sodium becomes a sodium plus, it becomes a cation. So system will change. System will change. You get the peak, sodium 1s peak, more resolution spectra compared to the previous survey spectra. And the difference between this energy to Fermi level energy is nothing but the binding energy. But if you see the agar electron, that is a secondary electron. So electron is ejected from 2p as to fill the vacancy, and one more electron is ejected from 2p. So this energy gap between this cell, valence cell, and Fermi level is a smaller. So it requires a less kinetic energy, less binding energy and therefore the binding energy of NKLL is a less than binding energy of sodium 1s. You can see here less binding energy compared to sodium 1s. So this is just to understand the how the binding energy difference will be observed. Okay, now as usual, 1 hour is almost over. Like yesterday, we will start to understand more detail about the XPS spectra. This is spectra from one research paper, XPS spectra of silver. This is a review paper, and to understand advances in the X-ray photoelectron spectroscopy to characterize, the review was written. So this is one of the survey spectra. This is a survey spectra. What is meant by survey spectra? Spectra starts with the zero binding energy and ends with the close to binding energy of incident X-ray. So again, definitely it is a aluminum K alpha spectra. And here we observed the number of peaks. Each peak is assigned valence cell 4D, less binding energy 4P. This next one is a 4S, very small. 3D, another 3D, splitting is there. Later on I will explain what is this 5/2 and 3/2, why splitting will be observed. 3P, 3/2 and 1/2, again splitting is there. 3S electron, and these are the agar electrons of 2s, which is not observed over here because whose binding energy is greater than 1400 electron volts, but the agar electron is observed over here. So this is a survey spectra, pure silver, how it is pure silver, how the spectra is observed. This is a high resolution spectra. So these two peaks is resolved into again high resolution. So this difference from very small difference can be elaborated, and we get the this 3D 5/2 and 3D 3/2. So we can easily analyze the binding energy difference between these two peaks, can be easily analyzed, and that difference comes to 6 electron volts. 6 electron volts. 368.3 is the 3D 5/2 binding energy plus 6 electron volts binding energy is for 3D 3/2. Next, this is for potassium chloride, aluminum K alpha XPS. Again, you observe this is chlorine, this is 2p electron of chlorine, 2s electron of chlorine. This is potassium, this is potassium, this is potassium. So if you took the spectra of potassium chloride, the potassium also emits the photoelectrons. This is potassium and this is a agar electrons. This is a survey spectra and this is a high resolution spectra. And again you can observe that splitting of 2p 3/2, which is not shown properly in the low resolution spectra or survey spectra. Splitting is there, but we cannot analyze properly. But if you took the high resolution spectra, we can easily analyze what is the difference between binding energy between 2p 3/2 and 2p 1/2 electrons. So that can be easily analyzed. That's why high resolution spectra is useful in the research purpose. So from survey spectra, we can analyze only elemental analysis. For elemental analysis, we can analyze spectra, how many elements and what elements are present in the given sample. That can be analyzed from the survey spectra. But for proper analysis and determination of structure, investigation of molecular structure, the surface area analysis, what kind of molecules are there on the surface of unknown sample research material. For that, we need a high resolution XPS spectra. Next, now what is about the 3/2 and 1/2 and 7/2 and 5/2, 5 by 2 and 3 by 2. So you might be aware about the RS coupling or spin orbit coupling or spin orbit splitting. This is a common terminology which are used in other types of spectroscopy. Earlier, you might be aware that NMR spectroscopy or Raman spectroscopy or ESR spectroscopy. You are aware about this spin orbit splitting, or we call it as a coupling. This is a quantum mechanical concepts, physics concepts concerned with the orbital angular momentum and spin angular momentum. And when we couple orbital angular momentum of electron with the spin angular momentum, then each electron in the L cell or P cell or D cell gives a two peaks because of splitting, like NMR spectroscopy. So this is one spectra, high resolution spectra, and it shows only one peak. This peak is for carbon 1s electron. And in case of carbon 1s, why it is not mentioned like 1 by 2 or 3 by 2, that I will explain. If you see the copper 2p, this is a splitted spectra, spin orbit splitted spectra, high resolution spectra. You observe clearly two different peaks having different intensity also. So in quantum mechanics, we can measure this intensity. Like in NMR, we measured the intensity by using Pascal's triangle. So every electron has a spin. If it is a unpaired, it is having either plus half spin or minus half spin. If it is a paired, the total spin becomes a zero. So either plus half or minus one half spin. And orbital angular momentum, old days in common quantum mechanics, it is called as a azimuthal quantum number, which is denoted by symbol L. So if our electron is from S orbit, then K cell or S orbit, which has a principal quantum number 1. But if it is a S orbit, their azimuthal quantum number is 0. If it is a p orbital, the azimuthal quantum number is 1. If it is a d orbital, azimuthal quantum number is 2. F orbital, it is a 3, and so on. So because of splitting of angular momentum of electronic orbit in S or P or D or F orbit with the spin of electron, then the line split up into two lines. Energy level split up into two lines. Here you can observe this 2p6 electron split up into L2 and L3 level as a 2p 1 by 2 and 2p 3 by 2. I think in inorganic chemistry, in the symmetry, you might have learned such type of notation. So if in this case, in case of copper 2p system, the electron is ejected, photoelectron is ejected from 2p orbital. So it's a principal quantum number 2p. So this stands a principal quantum number is 2. 2 stands principal quantum number is 2. And p orbital has an azimuthal quantum number 1. Azimuthal quantum number 1. And the electron which is present in that particular orbital either have a plus half spin or minus half spin. So L plus minus S, this is called as a spin orbit splitting. And by using this notation, we can find out the spin orbit splitting. So in case of 2p, the L value is 1 and S value is either plus half or minus one half. If it is a plus half, then 1 plus half will be 3 by 2. And if the spin is anti-clockwise of that electron, then azimuthal quantum number minus half will be half. 1 minus half will be plus half. So such type of splitting of energy level is called as a spin orbit splitting. Spin orbit splitting. So for S orbit, L is equal to 0, 0 plus half or minus half. So this is either plus half or one half. So which is not mentioned in the carbon 1s, not necessary to mention. But for copper 2p, split up into two peaks, one electron from 3 by 2 and one electron from 1 by 2. So electrons can be ejected, photoelectrons can be ejected either from this 2p orbital, suborbital, or from these two suborbital. So accordingly, you will get lines in the spectra, two different lines, two different peaks in the spectra. So that's why it is called as a denoted as a copper 2p 3 by 2 and copper 2p 1 by 2. So it means that electron is coming from 1 by 2 and 3 by 2. Again, here the intensity of line is also related to the whether from intensity of line also we can understand whether it is from p orbital or d orbital or f orbital. And if it is electron is ejected from p orbital, then the intensity ratio of half 2p and 3 by 2 to 2p orbital is 1:2, because here it has a 2 electrons and here it has a 4 electrons. So ratio becomes a 2:4 as a 1:2. 2:4 is nothing but the 1:2. So this intensity is, for example, 500 counts. This should be 1000 counts. So from that also we can judge whether this electron is 2p or 3p or 3d. It is coming from p orbital electron or d orbital electron. In case of d orbital, when electron is ejected from d orbital, then according to spin orbit splitting, it gets two different energy level, 5 by 2, d 5 by 2 and d 3 by 2. And again, the intensity ratio will not as a 1:2, it becomes a 2:3. In short, EZ level and T2Z level in terms of d orbitals. In case of f orbitals, the notation in spin orbit splitting is f 7 by 2 and f 5 by 2, which has an intensity ratio 3:4. So this intensity ratio is 3:4. This intensity ratio is a 2:3. This intensity ratio is a 1:2. So from that also we got some ideas about electron is coming from either f orbital or p orbital or d orbital. So that is the application of quantum mechanics, spin orbit splitting in the X-ray photoelectron spectroscopy. Okay. Now, one more important concept is a chemical shift. Yes. Can I?
Sir, I have one question.
Okay.
Sir, elements from the same period,
Uh,
how we can differentiate through this spectroscopy?
okay. Next slide is the same. Wait for 2 minutes for your answer. Okay.
Okay, sir. Okay.
Okay. Chemical shift. See here, we are shifting same periods, same rows. This is same rows: boron, carbon, nitrogen, oxygen, fluorine. Electronegativity increases from left hand side to right hand side. Fluorine is more electronegative than oxygen and nitrogen and carbon, and respect to boron. So here I am showing some functional groups. In fact, in the next slide, I will explain in detail some functional group. When carbon in our surface system is bonded with boron, or it is bonded with hydrogen, or it is bonded with another carbon with single bond, which we call normally as a hydrocarbon. General functional group, we call it as a hydrocarbon. 1s binding energy of this carbon 1s binding energy of this carbon is 285 electron volts. In case of carbon which is attached to nitrogen, amine nitrogen, compared to carbon, compared to hydrogen, compared to carbon, this nitrogen is more electronegative than carbon. So this, because of more electronegativity, this property you had studied in inorganic chemistry. So this 1s electron, if you see that the binding energy increases from 1 electron volts. This is 1s binding energy of carbon, and this is 1s binding energy of amine carbon, but having difference 1 electron volts. So which means that to remove the electron, 1s electron of amine carbon requires more binding energy compared to normal hydrocarbon or carbon bonded with the methyl groups or carbon bonded with the hydrogen groups. Next, when carbon is bonded with alcoholic oxygen or ether oxygen, oxygen is again more electronegative than nitrogen. So this carbon again requires more binding energy. 0.5 electron volt binding energy is more. Similarly, this oxygen and chlorine is below the fluorine. The electronegativity of oxygen and chlorine is almost identical. So if the carbon is bonded with the chlorine, binding energy comes to 286.5, which is close to alcohol ether carbon. Then if the carbon is bonded to the next more electronegative row of first row, that is for fluorine, then again binding energy increases. So increase in electronegativity increases the binding energy. Not only the electronegativity, this is carbonyl carbon double bonded with oxygen. The binding energy again further increases compared to single bonded carbon with oxygen single bonded, which has binding energy 286.5, and here it becomes a 288 electron volts. So the constituents atom binds with either electropositive elements or electronegative elements, plays a very important role, and in like NMR spectra, in this spectroscopy, which is called as a chemical shift or elemental shift. We can say elemental shifts or chemical shifts. This is more detail of the organic functional groups. Hydrocarbon, this earlier I explained, carbon with amine nitrogen, alcoholic carbon or ether carbon, binding energy increases, carbonyl still binding energy increases. Acid carbon, functional group is a different. Carbon is attached to one side with the double bonded oxygen, another side with the oxygen, and the binding energy further increases. Then carbonates, CO3, calcium carbonate is there. Carbon bonded with 3 different oxygen, further binding energy increases. If carbon bonded with 3 different fluorine atoms, in case of CF3, then again binding energy increases compared to single CF bond, which is 287, and it becomes a 293.5 electron volts. So the bonding we can identify with the help of X-ray photoelectron spectroscopy. What kind of bonding we can determine with the help of such a analysis with the help of X-ray photoelectron spectroscopy, which requires precise literature knowledge of binding energy of each constituent elements, with the bonding with the electropositive or electronegative, or next slide is concerned with that student's question. Okay, next slide is there. Now this is one polymer. Polymer is a more than monomer. N number of monomer combines, which gives a polymer. So it is a repeating units, and here 3 different carbons, like NMR, exactly NMR. This carbon has a different environment. This carbon has a different environment bonding, and this carbon has a different bonding. And when we record XPS spectra, high resolution XPS spectra, you will observe interestingly 3 different peaks, intense peak, because polymer consists of large number of this carbon, large number of this carbon, large number of this carbon. So each carbon emits the electron, and the electron intensity of each carbon will be the higher. So more intensity will be observed. So first carbon, this blue color carbon, bonded with one more carbon, bonded with three different hydrogen, methyl carbon. We normally assign in NMR as a methyl carbon. This carbon has 1s binding energy. This carbon has a 1s binding energy, 285 electron volts, like previous slide. Now, this next carbon has a different environment. One side, the chain of polymer, which is oxygen, and another side, there is a chain of polymer, which is carbon. So, one side carbon, one side oxygen. One side carbon, one side oxygen, which has 1s binding energy, 287. The difference is 2 electron volts. 2 electron volts is a bigger number in the analysis of any sample material or any research material. Then this carbon, one side it is bonded with carbon, and it is also bonded with carbonyl oxygen and carbon oxygen single bond. Again, binding energy increases by 2 electron volts. So this plays a electronegativity effect role. Electronegativity effect roles. This shifts of binding energy from 285 to 287 to 289, which is called as a chemical shift in a X-ray photoelectron spectroscopy. Okay. Now maybe next slide. Next to next slide is your question answer. This is another organic compound having 1s carbon electron is shown in the high resolution spectra, and here also you observe 4 different carbons, and each carbon is showing different binding energy in the spectra. There is a shift in binding energy, 2 electron volts, nearby 3 electron volts, nearby 4 electron volts, greater than 4 electron volts. So such a shift is called as a chemical shift, since the environment of this carbon is different, environment of this carbon is different, environment of this carbon is different, environment of this carbon is different. Environment means different electronegative. Carbon is different atom is attached to the carbon with the double bonding and single bonding. So this is also interesting example for organic compound chemical shifts. This is one example of polymer. You see that this is a survey spectra, and in the survey spectra, 2 peaks are very intense, carbon 1s and oxygen 1s. These are the core share electron having higher binding energy. And when we took the high resolution spectra of carbon 1s and oxygen 1s, for oxygen 1s, it gets 2 more peaks as like a splitting. And carbon 1s gives a 4 different peaks. 1, 2, 3, 4 different peaks is observed in the carbon 1s spectra, which means that this polymer has different 4 sets of carbon and 2 sets of oxygen. Which 2 sets of oxygen? This is the first oxygen, this is